Have you ever hit save on a huge file? I'm talking about a big video, maybe a design document, and a second later, it's just there.
Yeah,
On your phone, your desktop, your coworker's machine, instantly, everywhere.
that feeling, right? That seamless digital magic.
Yeah, that digital disappearance act, we call it the cloud. But, when you actually peel back the layers, what's underneath, is it really, like the old internet joke goes, just magic file dust?
It's the exact opposite of magic dust. That instantaneous feeling you're talking about, it hides a system of just truly staggering complexity. It's robust. It's high-stakes engineering.
High stakes, how?
Well, when you're designing a system to handle billions of files, petabytes of user data, you're hitting these massive system design challenges that, frankly, they dictate everything, from your server choice right down to whether the business is even viable.
Okay, let's unpack this for you. We have been completely immersed in the system design documents for distributed file storage. This is the kind of architecture that runs the biggest file sharing services in the world.
Right.
So our mission today is to cut through all that jargon and give you the shortcut to understanding the whole system. We're focusing on the core components, how they scale up, how they guarantee data consistency, and this is the big one, how they deliver bulletproof fault tolerance.
And our sources today, they really go to the deep end. We're covering everything you need to know. The choice between different storage layers, the critical role of metadata management, the complexities of real-time sync, concurrency, and of course those essential fault tolerance mechanisms you need to stay online 24/7.
It's the full roadmap.
A complete roadmap of back-end engineering mastery. Yeah.
So let's start at the beginning, the absolute foundational building blocks. If we're going to build this global digital warehouse for billions of files, what are the primary pieces we have to put in place?
You need three primary components. Each one has a very specific, very optimized job.
Okay.
First, you have your storage servers. That's where the raw bits and bytes of your actual file are going to live. Second, you need metadata management. This is the brain. It's the index, the map of the entire system.
And the third.
And finally, synchronization services. These make sure that when you change a file on one device, all your other devices instantly agree on that new version.
Okay, let's look closer at that first one. The storage layer. When you say storage, you're not talking about like stacking hard drives in a server rack, are you?
No, we've moved way past traditional block storage for this kind of thing. Modern systems lean very heavily on object storage.
So things like Amazon S3 or Google Cloud Storage.
Exactly like that. The advantage here is that these systems, they're built from the ground up for inherent scalability and just incredible durability. They don't think of files in a folder tree. They just think of them as flat, unique objects that you can spread across thousands of servers.
So no central bottleneck.
Precisely.
So the raw file data, the photos, the documents, it all lives in this huge distributed object storage. But if I want to open, say, the deep dive script draft, how does the system possibly know where in that ocean of billions of objects my specific file is?
And that is the job of the metadata management layer, which is, arguably the most crucial component of the entire setup.
So this layer doesn't store the file itself.
No, it stores everything about the file. Its name, its size, who owns it, who has permission to see it, its version history, and most importantly, its exact physical location or its identifier within that object storage layer.
Okay, so it's like the difference between a library full of books and the card catalog that tells you exactly where shelf 3B is. And that card catalog, that index, it has to be blindingly fast, and it can never, ever fail.
That's the perfect analogy. This layer demands high availability, extremely fast lookup databases. You see systems like Cassandra or DynamoDB used here a lot. They're designed for just incredibly high throughput and low latency.
It makes sense.
Yeah, think about it. You might access a file once a week, but the system hits that metadata layer every single time you open the app, sync a device, or even check permissions. It has to operate at massive scale, instantly.
Okay, we have the storage and we have the brain. Now let's follow the user. Let's dive into the right path. The moment you click upload, this feels like the trickiest part of the architecture. How do you get a massive file into the system without everything just grinding to a halt?
It's a multi-stage process, and it's all designed for resilience. The journey starts when your client, your computer, initiates the upload.
Right.
That request, it doesn't hit a single storage server. It hits a load balancer first.
The traffic cop.
Exactly, the traffic cop. It distributes that incoming upload traffic across a whole cluster of dedicated write servers, just for pre-processing.
Okay, but what happens then?
Now here's the crucial step. That write server doesn't immediately try to write the file to object storage. Instead, it streams the file data, usually broken into chunks, into a message queue system, something like Kafka.
Whoa, wait. Why the detour through Kafka? Why not just send the chunk straight to S3 and be done with it? That feels like an extra step, an extra point of failure.
It is, but it's the difference between synchronous and asynchronous operations. And it's absolutely essential for the user experience.
How so?
The message queue enables asynchronous processing, and that is vital for any large upload. I mean, if we try to process a 2 gigabyte video upload synchronously, your app would just sit there, frozen, waiting. It would probably time out.
Ah, right. So by putting it in a queue, the system can immediately tell me, hey, we got it, and then do all the heavy lifting in the background.
Yes. The client gets an immediate success notification, and the system now has guaranteed receipt of that data. This is how you build a decoupled architecture.
So Kafka acts like a buffer.
A huge buffer.
Yeah.
It distributes the processing load across dozens, maybe hundreds of independent workers who just pull chunks from the queue. It prevents one massive upload from blocking the whole system.
That makes the system incredibly resilient. I mean, if a worker fails halfway through processing my video, the data is still safe in the queue for another worker to pick up. But hang on. If Kafka breaks the file into chunks and different workers are processing them, how do you guarantee they all get reassembled in the right order when they finally hit the storage layer?
That is a great question. That's where the messaging system's more advanced features like partitioned ordering come in. Every chunk is tagged with its sequence number and its file ID. The queue makes sure that all the chunks for the same file are processed sequentially, or at least that the final assembly mechanism waits until all the chunks are there before it finalizes the object.
It's a constant battle against concurrency.
All day, every day.
Right.
Once that reassembly is complete, the data finishes its journey and flows into object storage. Now it's stored, so we have to pivot to speed.
Right, because storing billions of files is useless if it takes 5 minutes to get one back. Let's talk optimization and security.
Speed is king, and performance relies on a really sophisticated, multi-layered caching strategy. It's all designed to reduce latency and protect the underlying databases from getting hammered.
And multi-layer means caching at different points.
Exactly. The outer layer is the CDN, the Content Delivery Network, like Cloudflare. This puts copies of popular files physically closer to you. So if you're in London, you get the file from a server in London, not Tokyo.
Makes sense. And inside the data center.
Inside, we rely on in-memory caching. Systems like Redis, they're used for lightning-fast retrieval of metadata, which reduces the need to constantly hit those big, heavy databases.
Okay, moving inward from there, let's talk about the gatekeeper, the Envoy proxy. What is a service mesh like Envoy actually doing when a request hits the cloud?
You should think of Envoy as part traffic controller, part security checkpoint. First, it's a service gateway. It handles authentication and authorization.
So it's checking my ID.
It's checking your ID, and it's checking that you have permission for the file you asked for.
Yeah.
That's a critical security layer before the request ever even touches the storage.
And its second job, routing traffic.
Yes. It operates as a reverse proxy. It intelligently routes requests to the right storage clusters. It can load balance across different regions, and it's constantly doing health checks on those clusters to make sure traffic only goes to servers that are fully functional.
That sounds incredibly robust. But what about a tidal wave? What happens if a celebrity shares a link and a million people try to download a file at once? How does it not just implode?
That's where Envoy's advanced stability features become the system's life support. Specifically rate limiting and circuit breaking.
Rate limiting is pretty self-explanatory.
Right. It ensures no single user can overload a resource. It protects against attacks or just, a massive unexpected surge in popularity.
And circuit breaking. That sounds like the big red emergency button, the fail-safe.
It's the software equivalent of a fuse box in your house. It's designed specifically to prevent cascading failures.
How does that work in practice?
So if one service, let's say a specific storage cluster, starts responding slowly or failing its health checks, the circuit breaker immediately trips. It isolates that cluster. This stops all the other services from hammering the failing unit, which lets the rest of the system operate normally while that broken part gets time to recover.
That brings us perfectly to the biggest challenge of all, scaling and fault tolerance. The whole promise of the cloud is that you never lose a file, which means you have to plan for failure, not just hope you can avoid it.
Absolutely. And the first strategy is simple. Sharding. You have to break up the data, spread the files across hundreds of thousands of storage nodes. You just can't fit it all on one machine.
But you can't just throw files onto random servers, right? If you add a new server, you don't want to spend the next 3 days moving half your existing data around.
No, that would be a nightmare. You need an intelligent map, and that map is often created using consistent hashing. Instead of a simple formula where adding one server messes up the location of every file, consistent hashing maps both the data and the servers onto a kind of conceptual ring.
So if I'm trying to picture this, if we add a new server to the ring, consistent hashing makes sure that only a tiny fraction of the data, just the stuff right next to it on the ring, needs to be moved.
That is the crucial insight. It ensures even data distribution, and it dramatically minimizes data movement when you scale up or down.
Yeah.
This prevents those disruptive performance hotspots that would cripple the system.
Okay, we've scaled it. Now for the core promise, resilience. How do we make sure that if a server literally catches fire, my file doesn't just vanish?
You mandate redundancy, and you do that through replication, typically triple replication. This means every single object, every file chunk is stored on 3 physically separate nodes, often in different server racks or even different data centers.
3 copies, that's a guarantee of availability, but
Anyway,
that's a huge cost, isn't it?
it's the ultimate engineering trade-off that defines the cloud business model. You are instantly accepting a 300% storage cost premium. Because the business liability of losing even one user's data is so much greater than the expense of storing 2 extra copies. If one node fails, or even if 2 fail at the same time, that third copy is still live and accessible. It's maximum resilience through planned, expensive redundancy.
Let's bring the circuit breaker back into this. If we have 3 copies, A, B, and C, and the cluster holding copy A fails, how does the system use that circuit breaker to self-heal?
Okay, so imagine storage cluster alpha goes offline, network outage. Immediately, the circuit breaker trips for alpha. Any new request that would have gone to alpha is now instantly redirected to copies B and C.
So the rest of the system doesn't even know there's a problem.
Exactly. It prevents the other services from wasting time trying to connect to a dead cluster. Service continuity is maintained.
So how does it know when it's safe to let traffic back to alpha?
The circuit breaker is always monitoring. It attempts these small, periodic health checks. Once those checks start passing consistently, showing alpha is stable again, the circuit breaker automatically closes. Traffic flows back, and the system starts re-replicating any data that might have changed while alpha was down.
It's all automatic. Hands-off resilience.
That's the goal.
That's just fascinating. The system fails safely and then repairs itself. But the engineers running this thing, they still need to know what's happening. Which brings us to observability. How do you keep a finger on the pulse of billions of transactions?
You have to monitor everything, constantly. System health depends on tracking key metrics. File access latency, is it slowing down in a certain region? Storage usage, are we about to run out of space? And most critically, error rates.
Are read errors spiking on one particular cluster?
Exactly. And this requires a whole dedicated stack of tools.
Right.
Prometheus is pretty much the standard for gathering these time series metrics. It scrapes data from every single component. That data is then visualized on custom dashboards in Grafana, which lets engineers see in real time where the load is spiking or latency is climbing.
And what if that Grafana dashboard lights up bright red at 3 in the morning?
That's where Alert Manager comes in. It's integrated with Prometheus, it processes those critical issues, and it pages the right on-call teams immediately. It ensures that the automatic defenses, like circuit breakers, are backed up by human intervention the second a real problem is detected.
So we've covered the whole journey, from that instantaneous upload confirmed by Kafka, through the secure gateway of Envoy, all the way to triple replicated storage that's protected by circuit breakers and watched by Prometheus.
And to sum up this whole deep dive, designing a reliable distributed file storage system for massive scale, it really boils down to tackling 4 non-negotiable engineering challenges.
Let's hear them.
Fault tolerance, so never losing a file. Efficient scaling, which is where consistent hashing comes in. Robust security, which is Envoy's job. And ensuring perfect data consistency across all your copies.
And that data consistency, that's the final frontier here, isn't it? We've established that triple replication means your file is on 3 separate nodes. It's highly available, but let's leave you with the ultimate engineering puzzle here.
If 3 different users, say, collaborators in different time zones, all try to edit the exact same document at the exact same moment, how does the system decide what happens? What mechanism ensures that all 3 replicated copies nodes A, B, and C converge on one single, correct, final version without losing anyone's work?
That concurrency control problem.
That is what separates a durable system from a truly reliable one.
Something to mull over next time you click that save button. Thanks for guiding us through the digital guts of the cloud.